Imagine landing a multi-billion-dollar rover on Mars. You have a start point, a goal position, and partly unknown terrain in between. This is not a normal pathfinding problem because the rover does not have a perfect map. It cannot see over hills, it does not know where every rock is, and it has no idea what hazards are waiting outside its sensor range. All it has is a local sensor radius. Inside that circle, it can update its map. Outside it, the world is still a prediction. So the real question is not just, what is the shortest path? It is, can the planner repair the path when the map turns out to be wrong? To understand how this works, we need to go through the evolution of pathfinding, Dijkstra, a star, and finally D Lite. Let's go back to 1956 in Amsterdam, where Dijkstra designed an algorithm that later became one of the foundations of network routing. The core problem is simple. Find the cheapest paths from a start node through a weighted graph. The logic is incredibly clean. The start node gets a cost of 0. Every other node gets infinity. Then we always expand the unvisited node with the lowest known cost. When we expand a node, we check its neighbors. And if going through the current node gives a cheaper cost to a neighbor, we update it. That update is called relaxation, which is just a fancy computer science word for we found a better shortcut. To turn this into machine execution, we use a priority queue. We initialize the start distance to 0 and push it into the queue. While the queue is not empty, we pop the cheapest frontier node, skip it if we already found a better route, and relax all of its outgoing neighbors. If a neighbor improves, we update its distance, record its parent, and push it back into the queue. That is the engine. Watch how Dijkstra expands. It floods outward like a wave. And as long as there are no negative edge weights, the moment a node is settled, its shortest path is mathematically guaranteed. That guarantee is why Dijkstra still matters, from network packets to logistics. But look at the search area. It is huge. Dijkstra is completely uninformed. It does not know where the goal is, so it can waste compute exploring in every cheap direction, even when the goal is northeast. In 1968, Peter Hart, Niels Nielsen, and Bertram Raphael introduced A*. They added a spatial estimate called a heuristic. The formula is f of n equals g of n plus h of n. G of n is the real cost paid so far. Is an optimistic estimate of the remaining cost to the goal. So A* does not just ask, how far did I walk? It asks, how promising is this direction? Dijkstra floods the graph. A* focuses the search. It still respects obstacles and terrain costs, but it explores fewer useless nodes because it has a compass. But there is one golden rule: the heuristic must be admissible. It cannot overestimate the true cost to the goal. If it overshoots, A* can return a fast but suboptimal path. Basically, wrong with confidence, but even A* has a catch. Standard A* assumes the map is known and static. For a rover, the map is still being discovered. So what happens when the rover is driving and its sensor detects a boulder blocking the planned route? The simple fix is to run A* again from the rover's current position. That works once, but if rocks, slopes, and hazards keep appearing, the robot spends more time replanning than moving. In 1994, Anthony Stentz introduced dynamic A*, or D*. The breakthrough was this: when the map changes, most of the old search is still useful. So do not throw everything away, repair only what broke. D* shifted pathfinding from creating a path once to maintaining a path while the world changes. Then in 2002, Sven Koenig and Maxim Lekachev introduced D* Lite. It keeps the same practical idea but with a cleaner structure. Each node tracks two values: G, the best known cost, and RHA, a one-step lakeout cost. When they match, the node is consistent. When they do not, the node needs repair, and D* Lite plans backward from the goal toward the rover. That sounds backwards, but it makes sense. The goal is stable. The rover is the thing moving and discovering new information. So D* Lite anchors the search at the goal, then repairs the route for the rover's current position as the map updates. This is the same family of ideas NASA used in Mars rover navigation. In late 2006, Field D*, a related D* variant, was uploaded to Spirit and Opportunity to upgrade their autonomous navigation capabilities. Now let's watch it run on our 100 by 100 navigation grid. Flat ground is cheap. Steep slopes cost more. Rocks are blocked. At the start, the rover's internal map is incomplete. It knows the goal and what is inside its sensor radius. The rover starts at the bottom left, targeting the beacon at the top right. A hidden rock cluster enters sensor range. The HUD flashes, obstacle detected, only 24 nodes are reprocessed. That number matters. The planner did not recompute the entire grid. It repaired the local damage. Next, the rover discovers a steep region. The HUD switches to cost map updated. The terrain is still passable, but now it is more expensive. So the planner does not just ask, "Can I go there?" It asks, "Is going there still worth it?" The path shifts again. Every detour, edge correction, and path repair shown here comes from the D Lite planner timeline. The video is rendered, but the route is not hand-drawn. The motion is driven by the simulation output. Finally, the rover reaches the beacon. Position 80 mode, goal reached. We navigated partly unknown, changing terrain, corrected the map on the fly, and avoided restarting the entire search every time.